but let me see.
Okay, now it's recording.
Yes, yeah.
Yes, excellent.
Okay.
And I see that I can share my slides, so you can go ahead and introduce me whenever you want. And
okay, yeah.
Okay.
All right.
And then how many minutes do you want me to speak?
Well, it's really up to you. If you want, you can do 45, 50 minutes.
Yes.
So,
45
10, 15.
And then 15 for questions. That would be good.
Yeah, that's right. Okay, perfect. All right, everyone. Today we have Professor Avi Loeb. He's the Frank B. Baird Jr. Professor of Science at Harvard University, as well as a best-selling author in multiple lists. He received a PhD in physics from the Hebrew University of Jerusalem in Israel at age 24, and he was the longest-serving chair of Harvard's Department of Astronomy, as well as the founding director of Harvard's Black Hole Initiative. Now, he's written more than 9 books, including the most recent Extraterrestrial, which is, if you haven't read it, I recommend you read it, as well as Interstellar, as well as writing over 1,000 scientific papers on a wide range of topics, everything under the sun, from black holes, dark matter, first stars, the search for extraterrestrial life, and so on. He's currently the director for the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics, and also serves as the head of the Galileo Project. Now, the Galileo Project, if you haven't heard about it, is the first systematic scientific search for evidence of extraterrestrial technological artifacts in our world. Now, I can keep going forever and ever. This is a really long list of things I can say about Avi, but without further ado, I give the stage to him. Thank you so much.
Thank you so much, Alfred. And I should make 2 corrections. First, you mentioned that I study everything under the sun. I wanted to correct and also mention that I study things beyond the sun, above the sun, so to speak. And the sun will not exist forever. Obviously, it has about 7 billion years left for its life, and we shouldn't refer everything to the sun because it's just a transient object. It doesn't have any importance in the big scheme of the universe. The second point I wanted to mention is that the simplest way to introduce me is as a curious farm boy. I was born on a farm, and I'm very curious about nature and haven't changed since then. So all the titles that I have are less important. So let me share my screen. I will show you some slides, and then feel free to ask me any question you might have. Okay, so here we are. And what I'll discuss today is a new frontier in astrophysics, which involves objects from outside the solar system. We call these interstellar objects. And the reason I'm interested in those is because there is a chance that we might see a tennis ball that was thrown by a neighbor. You know, if we look at our backyard among the rocks, we might find something that indicates that we are not alone. And of course, that's like finding a technological needle in a haystack of rocks, but it's worth the effort because we sent 5 probes to interstellar space so far over the past 50 years. These are Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. They will exit the solar system in 10,000 years or so. And then there will be space trash. They will not be functional anymore. And, you know, since most stars formed billions of years before the sun, it's quite likely that other civilizations existed before us, maybe by billions of years. That was enough time for any probe from them to have reached our neighborhood. And such probes keep accumulating over time, just like plastics in the ocean. So we just need to check. And actually, the first 3 interstellar objects were discovered only over the past decade. So you have a chance in your career to check future interstellar objects and figure out if they are technological in origin. This is a new frontier. The first object identified as interstellar was noticed on January 8th, 2014. It was an interstellar meteor, and a meteor means that the object collided with Earth and burned up in the atmosphere, creating a fireball. We gave it the name IM1. We discovered it with my student, Amir Siraj. And it was roughly 0.5 meter in size, the size of a watermelon. But it was very unusual, first because it was moving very fast, faster than 95% of the stars in the vicinity of the sun. And moreover, it disintegrated only when it was subjected to a very high stress in the Earth's atmosphere. So its material strength was tougher than all space rocks that were cataloged by NASA, 272 of them over the past decade. And that meant that it had also unusual composition, which by now we verified, as I'll mention. The second interstellar object was discovered on October 19th, 2017. It was given the name Oumuamua because it was discovered by a survey telescope in Hawaii. And this name means a scout in the Hawaiian language. It was roughly the size of a football field, 100 meters or so. And it didn't collide with Earth. It passed near Earth within about a sixth of the Earth-Sun separation. And it was anomalous in various ways. It was flat in its shape, pancake-like, at least 10 times longer than it was wide. And then it featured the non-gravitational acceleration without any evaporation. There was no rocket effect from any visible cometary tail. And so the question is, what was pushing it away from the sun? And it also originated from a special frame of reference, the local standard of rest, which is the frame of the Milky Way galaxy. And only 1 in 500 stars is so much at rest as Oumuamua was in that frame. And then in August 29th, 2019, a year and a half, almost 2 years later, there was another interstellar object. That one was a comet, very familiar, similar to the comets that we see in the solar system. It was given the name Borisov after the person who discovered it. This one was not anomalous. So out of 3, the first 2 were unlike the familiar rocks that we find in the solar system. And so that intrigued me as to whether they might be technological in origin. Now, what is an interstellar object? Just consider the sun and an object passing by at some distance r. So an interstellar object is an object that has a speed above the threshold to escape from the sun's gravity, from the solar system. And in the vicinity of Earth, that is 42 kilometers per second. The Earth is moving around the sun at about 30 kilometers per second. But if you just gave it square root of 2 more speed, it would escape from the gravitational pull of the sun. And so any object we see moving faster than that in the vicinity of Earth, we know it came from interstellar space because it cannot be bound to the sun. Now, as I mentioned, Oumuamua was actually recognized in 2017, and it was quite unusual in its shape, unusual in its push away from the sun without a cometary tail. And so I suggested that what's pushing it is actually the sunlight. And for that to be effective, the object had to be very thin, like a sail, except this one would be a light sail, but it could be just a surface layer of a bigger object. And nature doesn't make thin objects like that, so I suggested maybe it's artificial in origin, but we didn't have enough data to figure it out. So it remains an open question as to whether it was natural or artificial. In terms of a natural origin, all the suggestions made in the literature, there were 4 of them, all of these models suggested something we've never seen before, like a hydrogen iceberg, a nitrogen iceberg, a dust bunny, things like that. And a month ago, there was a new play that was presented about my research on Oumuamua. It was named A Piece of Sky, and the playwright plans to show it off-Broadway in New York City within a year. And let me just mention a few phrases from that play. One of them asks, why is childlike bullying more prevalent than childlike curiosity? And that is in reference to the way that many scientists responded to the possibility of an artificial origin to Oumuamua. They ridiculed it, they pushed back, they said it shouldn't be even considered. And my advice to young scientists like yourself is that you should never pretend to be the adult in the room. Maintain your childhood curiosity. So about 2.5 years ago, I established the Galileo project at Harvard University. And the goal is to study objects near Earth that could be of extraterrestrial technological origin. And in the first phase of the project, we constructed an observatory at Harvard University that has various components that I'll describe in a minute. It observes the sky 24/7 in the infrared, optical, radio, and audio, and the data is analyzed by machine learning to figure out whether we are looking at a bird, a balloon, a drone, an airplane, or maybe something else from outside of Earth. So here is a short video that describes the various components of this observatory.
Welcome to an overview of the Galileo project's development site, codenamed Pigeon Run. Our instrumentation suite consists of both wide field and narrow field sensors. Wide field sensors are used for target selection and tracking, while narrow field sensors gather higher resolution data on potentially anomalous objects. Our main instrument is DALEC, a hemispherical array of 8 infrared cameras. Next to it is the Alcor, a secondary high-resolution optical all-sky camera. Together, these instruments continuously monitor and track objects in the sky, analyzing them in real time for potential anomalous activity. This is AMOS, our acoustic monitoring omnidirectional system designed to detect and record acoustic signatures across the infrasonic, audible, and ultrasonic bands. AMOS also houses an ADS-B antenna for logging aircraft transponder data, allowing us to quickly separate known from unknown objects. Here we have Skywatch, a multi-static passive radar system designed to detect and track multiple objects simultaneously, measuring object positions and kinematics. And Pac-Man is an environmental monitoring system for measuring local weather conditions. Sensors include an anemometer, temperature and pressure sensors, a particle counter, and a flux gate magnetometer. Next up is Spectre, a radio spectrum analyzer with a wide band antenna for measuring radio and microwave emissions. Beacon is currently our only narrow field instrument. Beacon is a high-resolution pan-tilt zoom camera capable of 40 times optical zoom. Our instruments collect a wide range of data, all of which is fed to our computing enclosure housed beneath the DALEC and Alcor instruments. Here, data is processed and analyzed in real time. Objects detected and tracked by the wide field instruments are localized in 3D space and analyzed for unusual characteristics. Selected targets are then sent to the Beacon PTZ for follow-up observation. Finally, data is recorded to disk and uploaded to the cloud via Starlink. These combined systems comprise the current version of the observatory class system, with many refinements, additions, and upgrades scheduled for near-term implementation at Pigeon Run.
And in the future, we plan to increase the capabilities of this system by adding more instruments so we can triangulate, figure out the distances to some objects. We have actually a new site where we are assembling a copy of the system in Colorado, and we are planning to make more copies as soon as we get more funding. We are also using satellite data, looking at objects from above, not just from below. And that's data that is available from Planet Labs that is providing us. We are currently analyzing that data. And altogether, we have a plan as to how to expand the current operations of the observatories that we have. And we published about 8 papers so far describing the system, and now we're starting to get results, and hopefully we'll publish them in a set of papers in the coming year. We're looking for anomalies, objects that we cannot identify. But what I'll focus on today is an expedition that I led to the Pacific Ocean to look after the material from the first interstellar meteor. And I wrote 43 diary reports during that expedition that you can find on medium.com. Just search for Avi Loeb at medium.com. So the story starts from a detection by the US Space Command, the US government satellites, of a fireball from this meteor back in 2014. And in about 5 years later, we noticed the data on a NASA website and concluded that the object was interstellar. And then 3 years later, the US Space Command confirmed the assertion that this object came from interstellar space at the 99.999% confidence. So at that point, I decided to lead an expedition to look for the materials from this meteor. And the cost was about $1.5 million, but gladly there was a donor that agreed to support that mission, and we decided to go after this first interstellar meteor to figure out whether it was a Voyager-like meteor. Imagine Voyager colliding with a planet like the Earth and appearing as a meteor in the sky of that planet. And it would, in that case, it would have an unusual material strength because it's made of artificial alloys, and it would also have an unusual speed because it was artificially propelled. And the government data included the light curve from the fireball, which had the 3 flares separated by 1/10 of a second. And they all occurred in the lower atmosphere of the Earth, where the pressure is very high. And so we calculated that, in fact, this object was able to sustain and maintain its integrity to much higher stress than any other meteor in the NASA catalog, 273 of them altogether over the past decade. So that is quite intriguing. And moreover, it was moving faster than 95% of the stars near the sun, and so relative to the local standard of rest. So the question was, what was it? And the government gave us this error box that you see on the right-hand side that is roughly 11 kilometers on a side. And we wanted to narrow down the path of the meteor better than that. So we used data from a seismometer on Manus Island in Papua New Guinea that recorded the sound wave from the explosion. And just like in the case of a thunder, you hear the thunder after you see the light from a lightning, because the speed of sound is 1,000,000 times smaller than the speed of light. And so from the delay between the sound wave and the detection of light from the fireball, we could tell how far it was from the seismometer. And that allowed us to narrow down the path of the meteor to this strip that you see in red on the right-hand side. So we rented a ship that was fittingly called the Silver Star. And here are some photos from that expedition, and I'll describe more details later.
Thinking I am Where you are drifting, not still thinking I am. Where you are drifting, not still thinking I am. Where you are.
So these are the photos, and that's the team of about 28 people on the deck of the ship Silver Star. And behind us, you can see this A-frame that connected the cable from the ship to a sled that was covered by magnets that we dragged on the ocean floor to collect the molten magnetic particles from the surface of the meteor. So the hope was that because it was so tough, it was made of iron, and therefore when the explosion took place, it melted off the surface of the object, and we can find those millimeter-sized particles, they are called spherules, from the surface on the ocean floor. The depth of the ocean was about 2 kilometers, and the region that we surveyed was about 11 kilometers in size. And we were looking for millimeter-sized particles at the bottom of the ocean, the size of a grain of sand. It sounds hopeless, and indeed, for the first 6 days, we didn't find anything. But here are some images. In the middle and right-hand side, you can see the sled being brought out of the ocean and put on the deck, and then we would scrape the magnets for any magnetic materials. And on the bottom left and middle, you see me jogging at sunrise every morning. Just as I jog on land, I did it on the ship. And we had a filming crew that came with us for the trip. And the director said, could we film you one morning? I said, sure, go ahead. And they asked me to jog 3 times longer than I usually do. So I jogged about 9 miles for them, about 15 kilometers or so. But at the end, the director asked, Avi, it looks like you're running. Are you running away from something or towards something? And I said, both. I'm running away from some of my colleagues who have very strong opinions without seeking evidence. Those are the colleagues that argue that this meteor must be a stone. But I'm also, at the same time, I'm running towards a higher intelligence in interstellar space. So here you see the sled at the top with the magnets on it, neodymium magnets, and we were scraping the magnetic particles that were collected. Every run, we had 26 runs. And then we would dry them up and put them under a microscope, as you see on the left. Most of the material was volcanic ash, black powder that we could filter out with a mesh. So we were left with bigger particles. We also used the vacuum cleaners, you can see, to basically collect everything that was attracted by the magnets. So let me show you how the sled would work. This is from a video taken from a camera that was attached to the sled. And it's just like mowing the lawn. We would go, and keep in mind, this is 2 kilometers down in the Pacific Ocean. And we would go back and forth. Most of the material on the bottom of the ocean is muck, mud. It's not magnetic, but we would collect magnetic particles as we would move along. And one of the big challenges was to keep the sled on the ocean floor, because it would lift up as a result of the tension in the cable. But we managed to do that. And every now and then we would bump into something. In this case, you can see a big rock that we carried with us. And maybe it came from this meteor, who knows? We just couldn't, I mean, the sled itself could not keep it. But we are thinking about having a second expedition where we would pick up bigger particles. And so here are the 26 runs that we had going back and forth. And there were a few runs far away from the meteor path, which is shown in orange, because we wanted to collect also material from the background. So we can tell the difference between the region that was associated with the meteor and what is found elsewhere. And after the 6th day, we put some big particles under the microscope, and lo and behold, we found the first spheral. And I was thrilled. I hugged the person who found it, and because I knew that when I see an ant in the kitchen, I usually get alarmed because it means that there must be many more ants out there. And so indeed, we found 50 spherals. You can see the whiteboard, a picture of the whiteboard on the left side here. We found 50 of them after the first one, and that was on the ship. And then when we brought the material back to Harvard University, we found many more. So here is how a spheral looks like. You can see it where the arrow is pointing. It looks very distinct from the background sand. It looks like a metallic marble. And we picked them up with the tweezers. And here are some images from the microscope as we looked at them. My daughter asked me if I can thread one of them and put it on a necklace for her, but I explained these are smaller than a millimeter in size. It's very difficult to thread them. They're very tough, actually. And then we put them in vials, sort of like babies that were just delivered. We put the vials in a white basket and then shipped it by FedEx to my home. And you can see the case on the right side after it arrived to my home, and I opened it up. I realized that a few days of delay because of the shipment by FedEx is not a big deal, because this material waited for perhaps billions of years before it arrived to Earth. On the left, you can see us checking the magnets on a rainy night. So then I brought the materials to a laboratory of my colleague at Harvard named Stein Jacobson, and he's a geochemist, and he has mass spectrometers that could analyze the composition. And he's standing here on my right, and then on the other side, you see a summer intern, that Sophie Bergstrom, who worked with me during the summer. And she discovered of all the 600 spherals, about 10 times more than we found on the ship. And so I called her the spheral hunter. And she did a fantastic job. And then we started analyzing those spherals in the mass spectrometer. These are photos of the spherals that she found. One thing we did was create a map. Actually, my postdoc, Laura Domini, did that. A map of the yield of spherals. And what you see in the yellow region is, in the yellow color, are, regions where the yield was about twice as much as in the purple regions. And on the left, you can see the zoomed out map where you can see that the control regions had a purple color and far away from the meteor site. But in fact, we found more spherals along the meteor path than you usually see in the background. So that was an indication that we were in the right place. And then in those regions, the yellow regions, we found a special type of spherals. So we took images with electron scanning microscopes of the inside of some spherals. And what we found are spheres inside spheres. So the idea is that the smallest spheres condense first and they solidify, and then they get engulfed with molten iron that binds them together into a bigger sphere. And this is an example of a spheral that looks like a soccer ball. And here is one that is the merger of three spherules. And what we found is this spherule in particular was in a yellow region and was of great interest to us because it was one of the largest and had a lot of material. The amount of mass that we have in a spherule is obviously proportional to the diameter cubed. So a spherule that is twice as large as another one has 8 times the mass. So that's why the biggest ones were of most interest. And this one in particular, and the first thing we checked was the iron isotopes. We found that it's very different from rocks that are found on Earth or even on Mars or the moon. But then we looked at the element abundances, and we found that relative to the standard composition of the solar system when it started, which is represented by 1 here in the vertical axis, there are many elements that are very enhanced. So what you see on the horizontal axis is the list of elements in the periodic table, starting from lithium all the way to uranium. And elements like beryllium, lanthanum, or uranium are hundreds of times more abundant than the standard solar composition. And that's very unusual. That was never seen before among spherules on Earth from meteors. And so we suggested that this composition is indicative of an extra solar composition of an object that came from outside the solar system. So here are 5 of those spherules that show this special composition. We called it the Belau composition for beryllium, lanthanum, and uranium. And here we plot it versus volatility. So elements on the right-hand side can easily evaporate when exposed to an airburst, to a fireball. And indeed, we find that there is a depletion in the abundance of elements that are volatile. And that indicates that these Belau spherules came from an explosion in the atmosphere. They came from a meteor. Question is, where did they come from to Earth? And how do you make such an unusual composition? And one way to do that in a natural way is to have a magma ocean, basically a planet that has rock that was molten on it. And actually, the Earth started as a magma ocean because it was bombarded by collisions early on. And one of those collisions generated the moon, which started as a magma ocean as well. And Mars was also exposed to such collisions and started as a magma ocean. And what happens in a magma ocean is that there is an iron core very often to such a planet, and elements that are attracted to iron, they sink, they segregate and sink to the core. And so they leave behind in the crust of the planet those elements that we found pronounced, like beryllium, lanthanum, and uranium, which are not attracted to iron. So that's one way to get it from a natural source. And the question is, how do you get a magma ocean planet to eject rocks at such a high speed as we observed, faster than 95% of the stars in the vicinity of the sun? That's about 60 kilometers per second. And at first I thought it's really impossible, but then I realized that the most common stars are actually dwarf stars that weigh about 1/10 of the mass of the sun. And the sun, if you bring the Earth close to the sun, it would raise tides on the Earth, just like the moon does. You know, the moon attracts the oceans, and that gives rise to the tides in the ocean. But if you put the Earth next to the sun, there would be even stronger tides, but they will not be strong enough to break the Earth. And the reason is simple, that the sun is not denser than rock. It's actually less dense than rock. It's about 1 gram per cubic centimeter in density, where rock is more like a few times that. So the sun cannot break the Earth by gravity. But if you consider the most common stars, which are not like the sun, these are dwarf stars like Proxima Centauri, near the sun, the nearest star to the sun, it's 12% of the mass of the sun. So dwarf stars that are a tenth of the mass of the sun are also a tenth of the size of the sun, and they end up being 100 times denser than the sun, because the volume goes like the size cubed. So when you make them 10 times smaller, they are 1,000 times smaller in volume, and altogether 100 times denser than the sun. So they can break up the Earth. They can destroy the Earth, disrupt the Earth, if it were to pass close to them. And indeed, we see planets around Proxima Centauri. And if such a planet comes very close to Proxima Centauri, it would get ripped apart and also will get molten. So perhaps these environments are the ones producing interstellar objects. And here is a simulation that shows how a planet like the Earth is getting spaghettified. It's converted into a stream of rocks. And half of the mass will be ejected to interstellar space. And we calculated at what speed. And we found that it's very likely to come out at a typical speed of 60 kilometers per second, which is the speed that this first interstellar meteor had, IM-1. So altogether, this implied an interesting scenario for making objects like this first interstellar meteor. And we calculated the rate and found that if you eject about 10 times the mass of the Earth worth of rocks per star in the Milky Way galaxy, you will get a collision of one of them every decade with Earth. And these are rocks that are about 500 kilograms, like roughly half a meter in size, the mass of this first interstellar meteor. So we find around dwarf stars, we find about 10 times the mass of the Earth near Proxima Centauri, near TRAPPIST-1. So it's a reasonable number. And then if these rocks get excited into an orbit that passes close to their star, which can happen if the star has a companion in the form of another star or a Jupiter-like planet, then those rocky planets can be disrupted when they pass close to the dwarf star. So altogether, the expedition was very risky because we had to get funding at $1.5 million. I had to recruit the expedition engineers and navigators. We had to build the machinery to accomplish the task, this sled. And for example, the sled could have not been on the ocean floor and not collect anything. That was a challenge. We might have not found any magnetic spherules from IM-1 on the ocean floor. Also, there might have not been enough of them. If the meteor was smaller, that just wouldn't be enough for us to find among the abundant magnetic particles from the background. And also, after we came back, we might have not had access to a mass spectrometer that allowed us to detect the Belau abundance patterns. So many challenges, but it's in life, it's always good to be an optimist because life is sometimes a self-fulfilling prophecy. And so the next expedition that we are thinking about is to find larger pieces of the object, just to figure out whether indeed it was a rock from another planetary system, or maybe technological, if we find pieces of a technological gadget that have, for example, buttons on them. The question is whether we should press a button. And just to summarize, here are my guiding principles. If you want ever to follow your curiosity, the most important thing is to follow scientific evidence by collecting data with instruments that you fully understand. that are under control and that are well calibrated. And it's also important to follow the principle of FIFA, the International Football Association, which is you can listen to eyewitness testimonies, but you must use cameras to make up your mind. And that's what we are using in the Galileo project. I mean, not only cameras, but we are using a mass spectrometer. We are using instruments. Because you cannot trust what people tell you. They are often motivated by their own agenda, and that includes experts. Then another important principle from sports is what is advocated by basketball coaches. Keep your eyes on the ball, not on the audience. And I don't know if, I mean, you must be very young and therefore you may have not noticed, but there are many people who pretend to be pro-science, but when they see facts that disagree with their models, they say that they ignore those facts. So they say they are protecting science, but what they're really protecting is their own prejudice. So if they have a model or an idea for something, let's say they think that everything in the sky, all the objects must be stones. I call that the Stone Age of science, where everything in the sky must be stones. So suppose they have a model for that, then anything coming into their telescope in the sky would be stones. And if the data doesn't agree with their model for stones, they would argue that the data is invalid. And I'm not making this up. Actually, when I came back from the expedition, there was a paper published in the Astrophysical Journal by experts on space rocks, and they said that the data from the US government must be wrong because it doesn't agree with their model for stones. And then most importantly, never mud wrestle because it will get you dirty. So if there are people that try to bring you to a low-level argument where they call you names or say things, just ignore them. And then the most important advice is to rise to the greatest heights of scientific practice where the oxygen level is too low for critics to continue what they're doing. So I'll be delighted to answer any questions you have. Please go ahead.
Is the floor open? Sorry.
Yes,
Yes, please,
floor is
please.
open.
Yeah,
Okay.
just yeah, let's go ahead.
Yeah, I was thank you so much for the talk. It was really interesting, and I've been very, very interested in reading about this work over the last few months. One question though that I did have is about the control area that you.
By the way, who are you? Can you introduce yourself?
Oh, my name is James. I'm a PhD student studying under Dr. Jeremy Lim, who I think is also attending. So my research is on at the moment I'm looking at outflows at high redshifts, galactic outflows.
James,
Okay.
James, sorry to break in. For people asking questions, it would be nice if you switch on your camera so Avi can see who you are.
Hold on, let me just put
And
my
also,
camera.
when you introduce your name, you can also mention your last name. So I will, when I see your papers, I know who you are.
Yeah, so I'm James Nyanias. Yeah, this is me. I think you can see me now.
Okay.
But yeah, so I was sorry, it's a bit dark in here. But yeah, I was just wondering. So this control area that you trawled on the ocean floor, did you verify that the properties of the ocean floor there are the same? Is the depth the same geologically? I mean, is it comparable to the area that where you found the spherules? Because I guess the first thing you would think is, oh well, maybe there's just something different, geologically different about the place where you trawled.
Right. So we surveyed, I mean, the control regions that we went to are tens of kilometers, 20, 30 kilometers away from the meteor site. And they were roughly at the same depth. there wasn't much difference in geological activity. Now, obviously, we expect the region that we did survey near the meteor path to contain some background. I mean, in fact, we do see that there are spherules in the yellow regions that are from the background that are the same as we find in the control regions.
Right.
So it's always a mix. But we do find so far that the Belau spherules are, I mean, we have a small number of them, but they were only in the yellow regions. But we are now in the process of going through 90% of the samples. So in the first paper, we just described what we found for a tenth of the sample, because it took us 2 months to go through that. And now we are sort of making the process more efficient. So we hope that within a few months we'll finish everything, and then we can report all the, the results for all the spherules. But the idea, I mean, we have of the order of 700 spherules altogether. So that means we might have of the order of 50 or 60 Belau spherules. And that will give us good statistics. If we find them also in the control regions, then it would mean that it has nothing to do with the meteor, indeed. And but we do find in the meteor site and elsewhere, we find, a large abundance of things that are from the solar system. These are well-recognized abundance patterns that we identify with standard meteors from asteroids in the solar system. And the closest to the composition that we find is the composition of rocks from the moon. But rocks from the moon are 1 in 1,000 in terms of the meteor abundance on Earth. And so they're extremely rare. It's really rare to find them. But what we find is was never seen for rocks associated with Earth, the moon, or Mars. And when I say that, I mean quantitatively, because there were lots of people who tweeted and argued, oh yeah, we actually found a paper where you see those elements. But look at the vertical axis. So it's a logarithmic axis, and we're talking about hundreds of times more than the standard solar composition. These people that were criticizing us as saying this is common were pointing to, of course, abundance patterns that we see all over the literature that are 10 times or several tens of times more than the standard solar composition, not hundreds of times. Okay, so the key is to look at the number, okay, or the vertical axis. Obviously, we're not claiming new elements in the periodic table, so obviously these elements were seen before. Okay, and obviously they were seen to fluctuate in different environments. But what we are saying is that the Belau composition was not seen before, where uranium is 600 to 1,000 times the standard solar composition. Now, I'm not saying it's necessarily artificial. In fact, in the latest paper, as I mentioned in my talk, we identified a natural scenario for a magma ocean near dwarf stars that could potentially make those abundance patterns. But it remains to. I want to go through the entire spheral sample before we have any definite conclusions on what it might represent.
Right. Okay. Thank you very much.
Sure. And keep up your work on the outflows, because I think, in fact, I wrote a paper on the fact that there are some active galactic nuclei that are claimed to have a higher abundance at high redshifts based on the Webb telescope data. That seems to be a very fashionable idea these days, but I think these are not the active galactic nuclei. They're just outflows from galaxies at high redshifts that are mistaken for the broad lines of quasars, and they don't have X-rays for those galaxies, and indeed that would be consistent with outflow models. And we just wrote a paper with Hamza Padmanabhan arguing that if these were AGN, they would overproduce the X-ray background.
Oh, okay.
So,
Well, I'll look that up. Thank you.
Yeah, check with Padmanabhan and myself explaining why they cannot be AGN. But there are many papers, and we cite them, arguing that there is a large population of AGN. I think it's just outflow. I mean, most of them are just outflow.
just star formation driven. You mean, yeah.
Yeah, I mean, they see broad lines and associate the broad lines with the broad line region.
Right.
Of
Okay. Yeah.
of a
Yeah. I
black
see.
hole. And And the point is, I think they're making a mistake because, and then they say, oh, well, if it's an AGN, it's an AGN for which the X-rays are blocked. But you can't have the X-rays blocked while seeing the other, the infrared optical emission from AGN. So to me, it sounds like they just misidentified. So you can include that in your thesis, the issue of a lot of outflows at high redshift.
I'm more star formation driven, kind of interested in my research, but I definitely have a look at it.
Yeah, I think that they are mistaken. So check it out. Okay, more questions. Don't be shy. You can ask anything.
Okay, let me switch on my camera. Hi, Professor Loeb. Thank you for your wonderful talk. I'm Jeremy Lim. I'm both Alfred's as well as James's PhD supervisor. I have many questions for you, many scientific questions, but I think I'll ask a question which is related to aspirations of some of the young people here. So you may not have noticed, but I actually wrote a recommendation letter for Alfred to work on Project Galileo with you. And that's because I think that all students should, all of us should follow our passions, our scientific passions. What I may not have mentioned in Alfred is my concern that you have experience with your colleagues, and I'm sure many other astronomers worldwide, that this is not a, I'm not going to put words in their mouths, but this is not a credible field to be working in. So I'm wondering whether you have advice for young people who want to follow their passion, who want to test scientific hypotheses, no matter how outrageous it may seem to other people, whether they should pursue these passions or whether they should be concerned that they may not be able to find an academic career after they do that.
Well, it really depends on the topic and the context, but I think you can have always a diversified portfolio, and the questions as to what proportion to give to well-established ideas and compared to more risky ideas. It's similar to the debate about in a financial portfolio whether how much risky stocks you should have in addition to bonds that might be more trustworthy, and we know that sometimes the markets are such that you lose money when you have bonds. That you can work on a subject that is considered popular for decades and then it will end up as nothing. I mean, there are many examples like that, but most recently, there is a large community of particle physicists working on string theory, hundreds of them, maybe thousands, and very brilliant young people engaged in string theory. But you ask yourself, okay, after 50 years, what did they deliver? They haven't made a single prediction that can be tested experimentally or that will be tested in the foreseeable future. Now, of course, they can impress each other and do mathematical gymnastics and get awards from each other, but that doesn't amount to new knowledge about the physical reality, which is the job of physics. And so you have a very sad situation of hundreds of brilliant people who spent decades of their career, the most prolific decades, on a mainstream popular subject. And it was popular simply for sociological reasons. There was no support for it experimentally, but it's just a large enough community decided that this is exciting and we should do that. And that is, you can get during those decades, you would get a job doing that. But at the end of your career, when you reach the age of 70, you would ask yourself, okay, what did I actually learn about the physical reality? And the answer may be not much. And to me, that would be very sad. So it's really up to you to decide how to split your time. And I would recommend a mixed portfolio where you have a number of areas, some of which, like let's say, somewhere between 2/3 to maybe 4/5, or so somewhere between 60% to 90% you can do at a young age, something that is popular, that a lot of people are working on. And the goal of that is just to impress your peers and show that you are qualified to get to a higher level in your profession. I mean, this is what I did. You have to dance to the tunes of selection committees. And, although I eventually became the chair of the astronomy department at Harvard for 9 years between 2011, 2020. And so I became part of the establishment, but it was never appealing to me as the highlight of my career. I really did that because I needed to demonstrate that I'm capable, and the only way to do that within the mainstream is to do what other people are doing. Okay, so you definitely need to do that, but at the same time, the rest of your time you can allocate to more risky projects, and the relative fraction of the time can change during your career. When you are a PhD student, you have to work with your mentor or advisor, so it may be a very small fraction, but when you become postdoc, you can allocate more time, eventually junior faculty, more time. And once you get tenured, I say, then you are free to pursue what really interests you, because so what happens to most people who get tenure? This is really unfortunate, but tenure was designed to allow academic freedom, to allow freedom of mind, so that you don't worry about job security when you pursue what seems right to you. But unfortunately, a lot of people, once they reach that point, they are still with the mentality of trying to gain honors and awards. And as a result, they try to please their peers and do whatever is popular. So unfortunately, the benefits of tenure is not practiced. Okay, and but what I would say is that once you reach job security, you should feel privileged to pursue, just like an artist, pursue the things that you're passionate about. Because what good does it make to have one additional person doing exactly what everyone else is doing? Like what? Okay, how? That will not benefit us a lot. It's better to pursue things that other people are not doing, so that maybe we missed something, maybe. And this way, the community, by searching over a broader space of ideas, would come across something really important. Nobody forecasted quantum mechanics. Nobody expected dark matter to exist. Nobody knows at the moment what is inside the black hole, what happened before the Big Bang. There are lots of things that could potentially surprise us. So I say we need those people who go in uncharted territories, and I really encourage young people with creative minds to innovate. You see that very prominently also in the commercial sector, in the private sector, which is surprising because it was supposed to be in academia, but in fact it's more prevalent in business, because when you have a good idea that seems to work, even if it's risky at the beginning, it could make a lot of money for the company. So they use this strategy of exploring ideas that might not be popular at the time, but could make them a lot of money. And it's a good investment strategy. They realize that. Otherwise, they won't do that. They want to make money. So if the business world recognizes that, why shouldn't academia recognize? I mean, that's the whole point behind the tenure. So what I say is always have a balanced portfolio. And, I wrote more than 1,000 scientific papers on subjects that were mainstream at the time, most of them, but I always pioneered something that I always tried to find something that nobody thought about. And I worked on the first stars, the first galaxies, when nobody cared about it. Now it's a very exciting frontier. I worked on 21 centimeter cosmology when not many people worked on that. I worked on imaging black holes when not many people worked. I worked on gravitational wave astrophysics, wrote many papers a decade before LIGO detected the first signal. And I remember giving a talk about gravitational wave astrophysics at a conference, a winter school. And as soon as I started, within 10 minutes, one of the professors stood up and said, Avi, why are you wasting the time of these students talking about gravitational wave astrophysics? This was 2012. Okay, 2012, in a winter school, December 2012, I gave an overview on gravitational wave astrophysics, and another professor who is 20 years younger than me, 20 years younger, stood up I mean, that shows arrogance for this professor to stand up. He stood up and said to me in front of the students, why are you wasting their time talking about gravitational wave astrophysics? 3 years later, gravitational waves were detected by LIGO, and the collaboration got the Nobel Prize for that. And now gravitational wave astrophysics is one of the most exciting frontiers. Now, what does it show you? It shows you that, first of all, before a frontier becomes prominent, you can find a lot of quote-unquote experts, people that represent science as it should be done, who would lecture you what to do and not to engage in something that is obviously now at the frontier. And moreover, that this guy who was younger than I am was telling me in front of students not to speak about this subject because I'm wasting their time. And moreover, a few years later, this becomes the most exciting frontier in astrophysics, the most exciting, with a Nobel Prize. So just think about the implications of that particular event. And that is just an example from many others that I have throughout my career. And so if I were back in 2012 thinking about what to invest my time, I would say, consider gravitational wave astrophysics, put some time. That's what I told the students at the time. And, obviously, if you were listening to my advice back then as a student, you would become, and in fact, I had some students working on that, you would become the world experts once LIGO detects a signal. So in fact, some of these students are now very prominent because they worked on gravitational wave astrophysics. They were ready for this new frontier.
Oh, okay. It's a very long answer. Thank you, Professor Loeb, for reminding us not to just follow the pack, but to follow the science, right? And
then you can lead the pack once the pack realizes that you are correct. I mean, this is the only way to make to discover new frontiers.
Right, and to remain childlike in our wonder for science.
Childlike, exactly right. Yes, never pretend to be the adult in the room. The one thing that adults often do is dismiss curiosity because it threatens their knowledge. They say, we know everything. We are respectable. How dare you even propose something we don't know? That's the adult approach. Never behave that way. Never. Because frankly, all we know is an island in an ocean of ignorance.
Right. Thank you so much, Professor Loeb. I'll give some time to other people to ask questions.
Thanks.
Professor Loeb, so it's been more than an hour. So if you're busy, you're free to leave. But
I have some other commitments, unless there is a very urgent question. If not, then it was a real pleasure to speak with all of you.
Sure. Does anyone have short questions? I saw Quentin put his hand up.
Yes, thank you, Alfred. Actually, your answer, Professor Loeb, I'm Professor Quentin Park. I'm director of the Laboratory for Space Research here at Hong Kong. I've been here about just under 9 years. And I take a lot of heart from what you said. I teach a course of paradigm shifts in science, and it's all about exactly what you're talking about in that last section that you spoke to, that people, there's a paradigm, there's an entire community set up around it. Nobody dared go against the existing paradigm. You have to wait for them all to die out, literally, before you can start this new area. But somebody like yourself that's so eminent and so successful, that's achieved so much already, you're able to risk more because you're very well established. It's much more difficult for younger faculty and postdocs to branch out into those areas because it is really going against the grain of mainstream scientific paradigm thinking, right or wrongly, and it's very risky for them. So I think once you're established and you've got a decent track record behind you, then your innate curiosity about areas you dared not approach before can now kind of be explored a little bit more. Anyway, that's just what I wanted to say because
I agree with you, and I often give the example of Picasso. Picasso, if you look at his early paintings, he made them realistic. And when asked about it, he said that he wanted to demonstrate that he can reproduce what people before him did. But once he gained enough stature, he started doing cubism, and all these the innovation came afterwards. So I agree with you, and I do think it's important that first to practice the way the field is done, and then secure a job, and then get more imaginative after that. So I believe that is the correct path. But as a young person, I remember having much more pressure internally for me. I just the difference between what I really want to do and what I have to pretend as if, you know, I'm in compliance with the standard thinking, that tension was much stronger, and I wasn't happy at a young age, I must say. So I'm actually happier right now because I don't give a damn about what other people say when they push back, you know, and I don't need them. But yes, as a young I never changed, you know. I had, in fact, I was thinking more outside the mainstream as a young person, and it was difficult for me. But gladly, I ended up in a situation where I can manifest my interests. So I very much hope that any person on this call who has an innovative mind will end up in the same position.
Professor Loeb, before we let you go, if you were ever in the area, Hong Kong or somewhere close, please do let us know so we can actually invite you to speak in person. It would be
okay. I will be delighted to visit you. I will let you know. Yes, thank you.
Thank you so much.
It's a pleasure.
Okay, well, I guess there's a lot more questions. Maybe next time we should have a 1-hour Q&A. But thank you so much for the very interesting talk and for taking time out of your day to grace us with all this information.
My pleasure.
Yeah, have a good day. Have a good rest of the day.
You too.
Thank you.
Good night to you.
Thank you.
Bye-bye.
Thank you. Good night. Yeah.
Thank you.